Building structural cable, often abbreviated as BSC, refers to a type of cable used in grounding and bonding applications within a building's electrical system. The purpose of a ground wire, regardless of whether it's identified as a BSC or by another designation, is to provide a low impedance path for fault current to return to the source. This ensures that overcurrent protective devices such as circuit breakers or fuses operate quickly to clear the fault, minimizing the risk of electrical shock and fire. Grounding and bonding are fundamental safety measures outlined in the National Electrical Code, or NEC. The NEC specifies requirements for grounding electrode systems, equipment grounding conductors, and bonding jumpers. The term building structural cable implies that the cable itself is integrated with or directly connected to the building's structural components. This connection to the building's steel framework or other conductive structural elements provides a path to earth, enhancing the overall grounding system. It is important to understand the various components and terminology related to grounding and bonding. Firstly, the grounding electrode conductor connects the grounding electrode system to the electrical service equipment. This conductor must be sized appropriately based on the size of the service entrance conductors, as specified in NEC Table 250.66. Secondly, the equipment grounding conductor provides a path for fault current from electrical equipment back to the source. This conductor can be a wire, a metallic raceway, or other approved means. The size of the equipment grounding conductor is determined by the size of the overcurrent protective device protecting the circuit, as detailed in NEC Table 250.122. Thirdly, bonding jumpers are used to connect metallic parts of the electrical system together to create an electrically continuous path. This includes bonding metallic conduits, enclosures, and other non-current carrying metal parts. Bonding jumpers are sized according to NEC Section 250.102. Different types of grounding electrodes can be used, including ground rods, ground plates, metal underground water pipes, and concrete encased electrodes, also known as UFA grounds. The selection of the appropriate grounding electrode depends on site conditions and local requirements. The NEC specifies the minimum requirements for grounding electrode systems in Section 250.50 and subsequent sections. Ground rods must be at least 8 feet long and driven into the earth. The spacing between ground rods must be at least equal to the length of the rod. Metal underground water pipes can be used as grounding electrodes if they meet certain requirements, including being electrically continuous and having at least 10 feet of direct contact with the earth. Concrete encased electrodes must be at least 20 feet long and encased in at least 2 inches of concrete. The size and type of grounding and bonding conductors are crucial for ensuring effective fault current clearing. Undersized conductors can overheat and fail to provide a low impedance path, while improperly installed conductors can create ground loops or other issues that compromise the integrity of the grounding system. The NEC provides detailed guidance on the sizing and installation of grounding and bonding conductors in Article 250. Proper grounding and bonding are essential for protecting people and equipment from electrical hazards. A properly designed and installed grounding system provides a low impedance path for fault current, minimizing the risk of electrical shock and fire. Regular inspection and testing of the grounding system are necessary to ensure its continued effectiveness. During these inspections, it's crucial to verify tightness of connections, check for corrosion, and measure the ground resistance. High ground resistance indicates a potential problem with the grounding electrode system and should be addressed promptly. Ground resistance testing is typically performed using a ground resistance meter, also known as a ground tester or earth tester. This instrument measures the resistance between the grounding electrode and the surrounding earth. The acceptable ground resistance value varies depending on the application and local requirements, but generally, a value of 25 ohms or less is considered acceptable for most systems. In addition to ground resistance testing, it's also important to perform visual inspections of the grounding system to identify any signs of damage or deterioration. This includes checking for loose connections, corroded conductors, and damaged grounding electrodes. Any issues identified during the inspection should be corrected immediately to maintain the integrity of the grounding system. The use of building structural cable as a grounding conductor must comply with NEC requirements for conductor size, material, and installation. The cable must be properly identified and protected from physical damage. Furthermore, connections to the building structure must be made using approved methods to ensure a reliable electrical connection. Specific sections of the NEC, such as 250.62, address the requirements for connecting to structural metal. In summary, building structural cable is a grounding conductor integrated with the building structure, providing a path for fault current and enhancing the overall grounding system. Proper installation, inspection, and testing are essential to ensure the effectiveness of the grounding system and protect against electrical hazards. Always refer to the latest edition of the National Electrical Code and consult with qualified electrical professionals for specific requirements and guidance related to grounding and bonding. When dealing with electrical systems, it's critical to understand the concepts of impedance and reactance. Impedance is the total opposition to current flow in an alternating current circuit, and it includes both resistance and reactance. Reactance is the opposition to current flow caused by inductance or capacitance. In a grounding system, low impedance is essential for effective fault current clearing. High impedance can impede the flow of fault current, delaying the operation of overcurrent protective devices and increasing the risk of electrical shock and fire. Therefore, it's important to minimize impedance in the grounding system by using appropriately sized conductors, making tight connections, and avoiding long conductor runs. Another important consideration is the concept of ground loops. A ground loop occurs when there are multiple paths for ground current to flow, creating a circulating current that can cause noise and interference in electronic equipment. Ground loops can also create a shock hazard if a person comes into contact with 2 points in the ground loop that are at different potentials. To prevent ground loops, it's important to establish a single point ground for the electrical system and avoid creating multiple ground paths. This can be achieved by using isolated ground receptacles and carefully routing grounding conductors. Surge protection is another critical aspect of electrical safety. Surge protective devices, or SPDs, are designed to protect electrical equipment from voltage surges caused by lightning, power line switching, and other transient events. SPD work by diverting surge current to ground, preventing it from reaching sensitive electronic equipment. The NEC requires the use of SPD in certain applications, such as dwelling units and critical facilities. SPD should be installed at the service entrance and at downstream panels to provide comprehensive surge protection. Different types of SPD are available, including Type 1, Type 2, and Type 3 devices. Type 1 SPD are installed at the service entrance, Type 2 SPD are installed at downstream panels, and Type 3 SPD are installed at the point of use. The selection of the appropriate SPD depends on the application and the level of surge protection required. In addition to grounding, bonding, and surge protection, other electrical safety measures include proper wiring practices, the use of ground fault circuit interrupters, or GFCIs, and regular electrical inspections. GFCIs are designed to protect people from electrical shock by detecting ground faults and interrupting the circuit. GFCIs are required in wet locations, such as bathrooms and kitchens, and in other areas where there is a high risk of electrical shock. Regular electrical inspections can help identify potential safety hazards and ensure that the electrical system is in compliance with applicable codes and standards. These inspections should be performed by qualified electrical professionals who are familiar with the NEC and local requirements. Furthermore, it's crucial to understand the concept of selective coordination in overcurrent protection. Selective coordination refers to the practice of coordinating overcurrent protective devices, such as circuit breakers and fuses, so that only the device closest to the fault opens, minimizing the impact on the rest of the electrical system. Selective coordination is particularly important to critical facilities such as hospitals and data centers, where a power outage can have serious consequences. Achieving selective coordination requires careful selection and coordination of overcurrent protective devices, taking into account their time current characteristics. Time current curves plot the time it takes for an overcurrent protective device to open for a given level of current. By comparing the time current curves of different devices, it's possible to determine whether they will coordinate properly. The NEC provides guidance on selective coordination in section 240.12. The selection of appropriate wiring methods is also an important consideration in electrical installations. Different types of wiring methods are available, including conduit, cable, and raceway. Conduit is a rigid or flexible metal or plastic tubing used to protect electrical conductors. Cable is an assembly of two or more conductors enclosed in a sheath. Raceway is a channel designed to hold and protect electrical conductors. The selection of the appropriate wiring method depends on the application, the environment, and the applicable codes and standards. The NEC provides detailed requirements for wiring methods in Chapter 3. In addition to these technical aspects, it's also important to consider the human factors involved in electrical safety. Electrical safety training is essential for all workers who may be exposed to electrical hazards. This training should cover topics such as electrical shock hazards, lockout/tagout procedures, and the proper use of personal protective equipment, or PPE. PPE includes items such as rubber gloves, insulated tools, and arc flash suits. It's also important to promote a culture of safety in the workplace, where workers are encouraged to report hazards and follow safe work practices. Regular safety meetings and training sessions can help reinforce the importance of electrical safety and prevent accidents. In summary, electrical safety is a complex and multifaceted topic that requires a thorough understanding of electrical principles, codes, and standards. By following proper grounding and bonding practices, implementing surge protection, using GFCIs, performing regular electrical inspections, and providing adequate electrical safety training, it's possible to minimize the risk of electrical hazards and protect people and equipment from harm. Always consult with qualified electrical professionals for specific requirements and guidance related to electrical safety. Furthermore, understanding the concept of arc flash is critical for electrical safety. Arc flash is a dangerous phenomenon that occurs when an electrical fault creates a high-temperature arc, releasing a tremendous amount of energy. Arc flash can cause severe burns, blindness, and even death. To protect workers from arc flash hazards, it's important to perform an arc flash hazard assessment to determine the potential arc flash energy levels. This assessment should take into account factors such as the voltage, current, and clearing time of the electrical system. Based on the results of the arc flash hazard assessment, appropriate PPE should be selected to protect workers from the potential arc flash energy. The NEC provides guidance on arc flash hazard assessments and PPE requirements in Section 110.16 and Article 130. Lockout/tagout procedures are also essential for electrical safety. Lockout/tagout is a safety procedure used to prevent accidental energization of equipment during maintenance or repair. This procedure involves disconnecting the equipment from its power source and attaching a lock and tag to the disconnect switch to prevent it from being turned on. Lockout/tagout procedures should be followed whenever work is being performed on electrical equipment to ensure the safety of workers. The Occupational Safety and Health Administration, or OSHA, has specific requirements for lockout/tagout procedures in its Standard 29 Code of Federal Regulations 1910.147. Electrical safety audits can also be conducted to identify potential safety hazards and ensure compliance with applicable codes and standards. These audits should be performed by qualified electrical professionals who are familiar with the NEC and OSHA requirements. The audit should cover all aspects of the electrical system, including grounding, bonding, overcurrent protection, wiring methods, and arc flash hazards. Any deficiencies identified during the audit should be corrected promptly to improve electrical safety. In addition to these preventative measures, it's also important to have emergency procedures in place in case of an electrical accident. These procedures should include instructions for shutting off power, providing first aid, and contacting emergency services. Workers should be trained on these procedures and should know how to respond in the event of an electrical accident. Regular drills can help ensure that workers are familiar with the emergency procedures and can respond effectively in a crisis. Finally, it's important to stay up to date on the latest electrical codes and standards. The NEC is updated every 3 years, and it's important to be aware of the changes and how they may affect electrical installations. Continuing education courses and professional development opportunities can help electrical professionals stay current on the latest codes and standards and improve their knowledge and skills. By staying informed and committed to electrical safety, it's possible to create a safe and productive work environment. Remember that electrical safety is everyone's responsibility, and by working together, we can prevent electrical accidents and protect people from harm. The NEC is a comprehensive document that provides detailed requirements for electrical installations. It's organized into 9 chapters covering topics such as general requirements, wiring and protection, wiring methods and materials, equipment for general use, special occupancies, special equipment, special conditions, communication systems, and tables and examples. Each chapter is further divided into articles, sections, and subsections, providing specific guidance on various aspects of electrical installations. Navigating the NEC can be challenging, but it's essential for electrical professionals to be familiar with its contents. The NEC also includes a number of tables and examples that provide practical guidance on applying the code requirements. These tables and examples can be helpful in determining conductor sizes, conduit fill, and other calculations. The NEC is not intended to be a design manual, but it provides the minimum requirements for electrical safety. The electrical engineers and designers must use their professional judgment to design electrical systems that meet the specific needs of the application while complying with the NEC requirements. The NEC is adopted by many jurisdictions as the legal basis for electrical installation. It's important to check with local authorities to determine which edition of the NEC is in effect and any local amendments that may apply. Local amendments may add or modify the NEC requirements to address specific local conditions. In addition to the NEC, other standards and regulations may also apply to electrical installations. These may include standards from organizations such as the Institute of Electrical and Electronics Engineers, or IEE, the American National Standards Institute, or ANSI, and the National Fire Protection Association, or NFPA. It's important to be aware of all applicable standards and regulations and to comply with them in electrical installation. Electrical work can be dangerous, and it's important to take precautions to protect yourself and others from electrical hazards. Always to energize equipment before working on it and use appropriate PPE. Follow safe work practices and be aware of your surroundings. If you're not sure how to do something safely, ask for help. Electrical safety is a shared responsibility, and we all have a role to play in preventing electrical accidents. The information provided here is intended for general guidance only and should not be considered a substitute for professional electrical advice. Always consult with qualified electrical professionals for specific requirements and guidance related to electrical installations and safety. Building structural cable is a specific type of grounding conductor, and its use must comply with all applicable codes and standards. Proper installation, inspection, and testing are essential to ensure the effectiveness of the grounding system and protect against electrical hazards. Always refer to the latest edition of the National Electrical Code and consult with qualified electrical professionals for specific requirements and guidance related to grounding and bonding. Understanding the terminology, principles, and practices of electrical safety is crucial for all electrical professionals and anyone who works with or around electrical equipment. By staying informed, following safe work practices, and prioritizing safety, we can create a safer electrical environment for ourselves and others. And always remember, when in doubt, consult with a qualified electrical professional.